What's up, you scholars of enlightenment? So last week we saw the release of the much anticipated Pentagon UFO report, which neither confirmed nor rejected the possibility that UAPs, or unidentified aerial phenomena, indicate alien visitation to Earth. Of course, predictably, the American government had no part in any of this. Now, the idea of intelligent life visiting our planet obviously captures the popular imagination and speaks to deep questions about the creation of life in our galaxy, the rise of technologically advanced civilizations, and ultimately, whether we're alone in the galaxy. So in a two-part special, Ramsey and I hope to discuss some of those questions and their implications with world-leading experts and understand the current cutting-edge thinking in some of these fields. So in the second part, we're going to interview UFO debunker Mick West, who has done the hard yards to catalogue, address and explain multiple UAP sightings and try to understand what we might be seeing in our skies. But in part one, we welcome back my good friend, Professor David Kipping, to discuss the possibility of whether life beyond our Earth exists in the Milky Way galaxy. Dave, welcome back to the channel.
It's a pleasure to be back on. Always good to see you, Sam, and thanks for having us talk about life in the universe, my favourite topics.
It's always a pleasure to have you here, Dave. Thank you so much for taking the time. Now, Dave is a professor of astronomy and head of the Cool Worlds Lab at Columbia University. So he's an expert in the hunt for exoplanets and also has a superb YouTube channel, the Cool Worlds channel, where he discusses some of these deepest problems and open questions in modern astronomy. I strongly suggest that you check it out, and all the links will be down in the description. So as we get into this, Dave, how do astronomers and scientists go about attempting to work out the likelihood of there being intelligent life in the galaxy? Have there been any formalizations of this?
I mean, it's a very difficult question to answer because science works based off evidence. And so what evidence do we really have for life in the universe? Practically nothing. I mean, really,
that's about it, right?
Yeah, so obviously we know about the history of the Earth, and we can look at the geological record of evolution and see how it played out on the Earth. We also know that we apparently don't see very obvious signs of intelligence in the galaxy. So we don't see stars that have been converted into machines very, clearly. We don't see the moon has been colonized by some alien species or something. So there's some very extreme limits we can place. But, we can't really say much about even the next star along because, how can you say just because you don't see a radio transmission, that means there's nobody there? At the end of the day, they could just prefer to hide themselves and not be very communicative. So it's pretty hard to say much. But of course, we know we keep getting encouraging signs, such as the fact that, of course, stars are extremely common in the galaxy and planets around those stars are very common. Earth-sized planets in the temperate zone appear not completely irregular, something like between 1 and 10%, depending on whose numbers you buy. So there's certainly planets out there. Of course, they could all be Venuses. For all we know, we didn't know the size, so we don't really know that they're hospitable for life. But we're getting to that step with the next generation telescopes where we might be able to actually probe their atmospheres and be able to tell, hey, could this planet actually be hospitable for life? And then maybe one day with direct searches we'll have some evidence. So it's all evidence-based, and we're very evidence-scarce right now.
So there has been one formalization that people sort of bang on and on about. You can probably see it now, and the viewers can see it, which is the Drake equation. Can you tell us a little bit about this and how useful it is? Because I guess, as you kind of said, we kind of have a dearth of evidence on this, even though this might be a formalization of that ignorance, if you like. Is that all it is, or is there anything more we can nail down in this?
The Drake equation is this extremely famous culture-esque level equation at this point that Frank Drake wrote down. And he really wrote it down to organize a conference. And I think the best way to think about it is how the famous SETI scientist Joe Tata, who was quasi-portrayed in the film Contact, Carl Sagan wrote, was really portraying Joe Tata. She described it as a way of organizing ignorance. And I think that's a good way to think about it. So if anyone could just plug in arbitrary numbers into this. So you can go ahead and say, okay, I think you've got the terms all written out here. I can do them very quickly. You've got R star is the rate of star formation in the galaxy. FP is a fraction of stars that have planets. NE is the number of habitable planets around each star. FL, those that form life. FI, intelligence. C, communication. And L is a lifetime of this communication. So N at the end, this big equals N, is supposed to be the number of radio signal pinging civilizations. But of course, it could be many civilizations which just don't radio ping. So you could just cross off the FC, and then you have all of the quiet civilizations. But look, we just don't know what to put in for these numbers. You could put in pretty much anything. You get numbers varying from 10 billion to less than 1, depending on how pessimistic you are. So nobody knows. Essentially, the last 4 of these are complete guesses, and arguably even the number of Earth-like planets is pretty uncertain at this point.
Interesting. So are there any? So we look at these as essentially a big, long, multiplicative list. Are there any of those numbers in there? You said it's a kind of lining out of our ignorance, things that we don't particularly know. Are there any of those numbers in there that we do know well in science? So are we moving in the right direction towards illuminating some of these corners of our ignorance?
Yeah, kind of. I mean, there's a lot of nuance with this equation if you go really deep into it. So take the first term, R star. You think, well, that's probably the one that is, by now we should really know that, the rate of star formation. But actually, it's not that simple, because it depends on what type of stars you're talking about. So when Frank Drake wrote this down, and most people who use it, they tend to limit it to sun-like stars, for which the rate is around 1 to 2, depending on and how you define sun-like. But more recently, people are thinking, well, actually, M dwarfs should perhaps be considered. These are smaller stars than the sun. They're the most numerous stars in the universe. And we're finding lots of Earth-sized planets around them. Proxima Centauri, for instance, has an Earth-sized planet in the haplozone around it, our nearest star. And so if you include those, then R star would be greater, because now you're including other types of stars. And so it ends up being like 10. So even that first term is controversial, because it depends on what type of stars do you consider to be habitable in the first place. Yeah. And then, of course, as you go along to the other terms, you could say, well, FP, surely we know that by now. Well, kind of. I mean, again, it's not so simple, because yes, we know there's lots of planets out there, but we've only seen the tip of the iceberg, right? Because our methods are always improving, our sensitivity is always improving, and so we're finding more and more and more all the time. And so even that number, we only really have a lower limit for. So it's, and then once you get to the FLs and FIs, I mean, this is, I've taken a stab at that. I've talked about that on my channel before. I read a paper about it, actually, and it's almost intractable. We had a paper where I calculated, just based off the evolutionary history of Earth, there is kind of this weird thing that might make you pessimistic, and that's that the timescale for evolution to get to complex life like us, and even just generally multicellular life, is of the same order of magnitude as the lifetime of our star, at least in terms of its habitable lifetime. So it's about 5.3 billion years, a window of opportunity, and it took us 4.4 billion years to arrive. So those numbers are curiously similar to each other.
Could that number could that number be different for different stars? Is that, or are you assuming that we're taking the one sort of data point that we have? Is that?
Yeah, so this is something that Brandon Carter pointed out, I think, like in the 90s or the 80s, that it's kind of a well-known issue that there's some curious coincidences with because stellar physics, stellar evolution really shouldn't have anything to do with evolutionary processes, at least very, very indirectly at most. And so it's kind of weird that the timescale for hominid brains to evolve is the same timescale that it takes stars to basically go through their main, or sun-like stars to go through their main sequence. But sure, if you go to M dwarfs, that timescale is very different. I mean, for M dwarfs, they live for up to 1 trillion years, even 10 trillion years in some extreme cases. Of course, the universe isn't old enough for us to have seen that happen yet, but we predict based off the rate of their hydrogen burning. Obviously, you can calculate their mass, so you know how much hydrogen they've got. They have such pitiful luminosities that unless something radically changes in their luminosity output, they should last for way, way longer than the age of the universe. And so in principle, that means there should be way longer for complex life to evolve, right? So if you have evolution might get stuck in a rut after 5 billion years, and it has to just sit there for 1 billion years stuck in a rut. But then, it gets perturbed. Maybe an asteroid impact happens. It kind of resets the clock and gives it another chance. So you would think that the more long-lived these stars are, surely that would be beneficial to the chances of emerging intelligent life. And yet, I wrote a paper about this also quite recently and did a video about it, that there's this red sky paradox. There's way more of these M dwarfs. They're much longer lived than us. They clearly have tons of planets. In fact, they seem to have more Earth-sized planets around them than Sun-like stars do, as far as we can tell. So it's kind of odd in a way. It's actually like 100 to 1 sort of ratio that you would naively expect, all things being equal, that you'd be born around M dwarf. So that doesn't prove that M dwarfs are uninhabitable, but it's just sort of a curiosity. Maybe it is fluke, but maybe it's telling us something deeper than that.
Maybe that our planet in some way is special. I think Ramsey had a question about this, didn't you, Ramsey, about whether this equation hides a lot of complexity about the types of planets around which, or the types of planet on which life develops, whether it requires a lot of additional ingredients.
One of the things that I always think about when I see the Drake equation, Dave, is like coming at this from the other way, and a bit like the rare earth hypothesis stuff of like, when we look at just how many flukes we've had as a species to get to where we are, is it actually that famous principle that like the only reason we can discuss and debate whether we're alone in the universe is because we are the only people that have actually made it to this point of stuff? Because there's all of these really subtle things like having a magnetic field, having had something wipe out the dinosaurs, because it's very unlikely that mammals would have got to the position we're in now if dinosaurs were going around eating us all.
But just be 3 T-Rexes sat here on OBS discussing like intelligent life.
There's an interesting thing I think about the size of different brains, right? So mammals have a very big brain compared to other things, and reptiles and fish and stuff don't. So if fish had dominated and stayed as like the dominant species, you wouldn't have fish as intelligent as we've become, and the same with reptiles. Just because of you can just kind of look at the ratio of brain size to size of body.
I'll believe you on the biology, because it's taken me 2 weeks to understand the SARS-CoV-2 genomic stuff for a video. So you can stick with the biology. I'll believe you.
Well, just the real topical thing right now, as well as I was thinking about it today and looking at the news, is like what's going on in Canada and the global warming stuff that we're all very conscious of. And we talk about the habitable zone and the Goldilocks zone and stuff, but if you think about it, every summer and winter we go from frozen water to hot enough to kill old people type temperatures, and that's just because our oblate spheroid is slightly tilted, but otherwise going on this precise orbit. And you kind of wonder, like, if we were just a fraction further away, would water be liquid long enough to be used? And if we're a fraction the other way, would it always be too hot for us to kind of survive properly and stuff like this? And what's the kind of thinking on the sort of rare earth hypothesis of how many flukes that we actually sit on? Ignore the Drake equation. Are we just a pure fluke?
Yeah, there's lots you've touched on there, and the rare earth hypothesis is totally viable in my opinion. So, when you mention like the tilt of the Earth, for instance, that's thought to be stabilized by the moon, which is freakishly large. So if you take away the moon, the obliquity of the Earth would vary as it does for Mars, and so you could end up with several million years where the North Pole is just pointing at the sun for 6 months of the year. So yeah, this would be pretty terrible for at least complex life, like doing agriculture. It's difficult to imagine civilization emerging where you basically ramp up those Canadian extremes to by a factor of 10 or something. So I agree that there's certainly lots of features there. I think the danger of too much of the rare earth hypothesis is, you can say, where does it stop? So you can say, well, we have about 3/4 of the Earth covered in ocean, and you could probably come up with some reason why that is a good thing for life, right? Maybe if it's completely covered in continents, then that you don't have the ability to have lids go under oceanic plates, And so you might shut off some of the plate tectonics. If you had completely ocean and there's no land for complex life to eventually take over the land. So there's some intermediate value, and we seem to be in this kind of nice sweet spot. So you could just keep going and going with all these things. And I think the problem is that we have this anthropocentric bias that we're looking at us almost as the peak and the pinnacle, and seeing all of these key moments where things fractured that eventually led to us, and saying, well, this is the only path. And the probability of each of those steps was small. So you end up with this tiny probability at the end of us arriving. But there could be a completely separate path over here that's just nothing to do with anything we know. So I think that's the slight danger of the rare earth hypothesis, is that it's very anthropocentric. It really looks at us as the model of how all intelligence must presumably emerge. However, having said that, I am completely open to it, and I think I'm often I often get criticism from many of my colleagues because I don't consider myself pessimistic. I say I'm agnostic about the possibility of life in the universe. But if you're going to be agnostic about it, which I think you really have to be as a scientist, since there's no evidence, that means you have to permit the possibility that we are alone in the galaxy. And a lot of scientists get really uncomfortable with that idea because they see the 200 billion stars in the Milky Way. 50% of them have planets. How could it, even if the percentage is 1 in a million, that would give you, many thousands of civilizations out there. So how could you possibly be pessimistic? But the problem is the probability could equally be, 1 in septillion, right? Or 1 in octillion, or whatever. You just pull out any ridiculous number you want, and by the weak anthropic principle, as you were alluding to there, you'd still end up with what we see, and it's no less or more likely than any other outcome because we don't know anything about abiogenesis, how life emerges, or all of this evolution yet because we have no data. So it feels kind of circular, but we really don't know that we could be alone. And I'm certainly open to it. And I think if you were not open to it, like, what's the point of even looking? In a way, I think you kind of shoot yourself in the foot a bit with the whole point of the experiment. Experiment should be there to find things out. And if you're claiming you already know, that's almost dogmatic, in my opinion. It's not really science. So I get pushback from that from my colleagues, but I really do stick to it, that we need to be agnostic about that question.
So what? Yeah. Looking at this equation, obviously, as you say, it was designed for a conference. It wasn't necessarily designed to be the be all and end all in this field, and it's taken on a life of its own. Has it kind of been, for want of a better word, abused? Because we see articles, maybe if you can see this one that's popped up here, that there are at least 36 intelligent alien civilizations in our galaxy, say scientists. This is on Forbes, and I've seen guesses that range from down to basically 0 all the way up to sort of hundreds of thousands of communicating civilizations in the galaxy. Is this just people shoving in their favorite numbers, or is there more to it than that?
Could we pause the recording for a sec?
Yeah, of course.
I can't talk about this paper.
Okay.
So this is totally off. This has to be off the record between us. But
maybe we should keep it for the end then.
We're live. We're
live, so shall I keep it for the end?
Okay.
All right, we'll keep it for the end. But yes, probably.
That's a good scoop.
So maybe if we just stick to whether this has been.
The thing I love about this though is I love this that there are at least 36 intelligent alien scientists in our galaxy. Say scientists.
I know. I'm making it sound like there's some conspiracy here.
It says, I'm watching X-Files at the moment,
really, and
it sounds like
it's just
Dave's like shushing me into a corner,
trying to be balanced, and I don't want to. I've sort of addressed this obliquely in other videos before, and I don't want to keep going at it because it might be too much for me to keep pouring cold water on it. So I recommend you see my previous videos about this, but I'm trying to be very conscious to not go on and on about this particular paper.
The interesting thing though is you get such huge ranges in these sorts of estimates, don't you? I think that's the key thing. It comes back to what we were saying before about the Drake equation. Like we could go and find a scientific paper that says 1, and we could go and find a scientific paper that says 200 or 2 million, didn't we? And
I mean, that was true of the original. I think in the original meeting, I mean, Carl Sagan was there. They had a few biologists there. They had some anthropologists there. I think they called themselves the Order of the Dolphin, and they all came up with different numbers, and it ranged by several orders of magnitude. And this is a pretty common thing that we do in intro level classes as well at Columbia and at other universities, where we give you the Drake equation, the students, and we get you guys to talk about it together and come up with your own estimates and justification. And you see it, like you can have different groups of students come up with wildly different answers. And the important thing is those students, their guesses are just as valid as anybody else's, because there's no evidence for what FL really is. So it's a complete black box in terms of most of those parameters right now.
Is there any sort of, so if we go back to the Drake equation, just as you said, it's a good way of organizing our ignorance. Is there any clear pathway forward? Obviously with R star we've got some idea, with FP we're doing exoplanet studies. Is there any technological and scientific pathway forward to finding out any of the other constants down the road? What is this sort of scientific roadmap for moving towards getting any answers to those unknown quantities?
Yeah, I mean, it's almost, I kind of worry it might be the wrong approach to try and nail down all of these parameters. I think it's good just as a sort of a broad brush mission directive type guideline. So we've built a mission to characterize FP. You might think of like the early exoplanet surveys of doing that. And then you got Kepler, which was sort of designed to characterize NE. It didn't quite get all the way there, but that was sort of its goal. And we are thinking of building telescopes like LUVOIR, HABEX. James Webb to some degree might maybe touch on this, of measuring truly the habitability of exoplanets and maybe even detect some life forms. But in terms of like, how do you do a survey to measure FC? I mean, it's almost inconceivable how you would ever do that. I think, the whole point of this is just to sort of say, there should be, I think Drake was kind of optimistic and Sagan was pretty optimistic. They thought there should be lots of civilizations out there. And in a way, this was a vehicle to justify that.
So that would mean you would be able to get a significant data set to be able to say, look at this civilization, this did this in this time frame, and this one did this. And then we can start to get some sort of statistical analysis going. But while we've only got one data point, we're sort of stuck not being able to do anything. Is that a fair assessment?
Yeah, and I think just the whole point here, we're all just in the same thing, is trying to answer the question. And rather than getting too hung up on the individual parameters, if you want to answer the question, just go out there and look for life and see how often you can find it. If it turns out that you survey 100 Earth-sized planets around sun-like stars that are the same age as the sun, and everything's as similar to the Earth as it can be, and all of them appear devoid of biosignatures, that's probably telling you something about, that's probably the best we could do. And similarly with SETI, they're trying to almost go right to the end, right? So SETI don't worry about solving these parameters. They're just trying to detect an alien civilization directly through their radio communications, or even more broadly through laser communications or other techno-signatures. And so you're kind of jumping the line. You're just going straight to the thing you really care about. And
not worrying about the sort of theoretical structure of
the framework so
the
much.
framework.
Yeah.
I think Ramsey had another question in here about how best it would be to, or how we might detect the presence of life on these exoplanets.
Yeah, well, actually, something you're just saying made me realise that there's something built into the Drake equation as well, that because it talks about radio, and actually there's a quite a big difference between intelligent life and intelligent life being able to generate radio waves, because of being able to work with electromagnetism. If you think about just our own history of what stage we reached, that was only like the last 150 years, but you'd argue that during the Renaissance period, the Dark Ages, during people sailing across the world, there was no use or knowledge of electromagnetism. And actually coming back right around to what your rocky planet happens to have on it. There's aspects of how we've been able to generate electricity and go on to use radio that if you didn't have certain components in your planet, you wouldn't actually be able to. I mean, an extreme example is that you couldn't have discovered or used any nuclear fission if you weren't in the right bit of your galaxy, in your solar system, for those heavy elements to be naturally deposited on the rocky planet you're on. So there's some bits baked into this as well, that because you're talking about radio, it will actually, that method of communication, it will actually exclude some of the intelligent life. But there was the one thing I think I was trying to ponder when we were setting this up and talking about UAPs. I couldn't find, and correct me if I'm wrong, and I just didn't look long enough, but I couldn't find the kind of Drake extension or someone else's equation for trying to assess whether there's the probability that we would be visited by UFOs, in effect, by other people. And I wondered if you can't nail down N properly because of all of the things we've just discussed, but if you hypothesize that it has a value, we just don't know what it is, do you reckon you can start to argue that given the Drake equation is N, an unknown value, then starting there, the probability that you go the extra technological steps beyond radio to actually being able to travel the distances and visit, do you reckon because we understand some aspects of those technological leaps, we could start to say that if the Drake equation answer is N, then the probability of being visited is 1,000 N or 10 to the minus 6 N, etc. Do you think there's being able to bound like that? Or is anyone, did I not look far enough? Is there
you're right, there isn't, I don't think there's a Drake equation equivalent, but a couple of thoughts about that. One would be that, I mean, for L, even if you focus just on radio, which I think just to advertise, we do more broadly think about this now. We think about optical signals and other types of signals as well. But L for radio is probably 0 for us. Like we just don't produce, there's never really been a campaign to systematically send out messages into the sky. We've sent out like 3 or something. It's just like a really pathetic number sent to a very specific star for like a minute. And if they weren't looking at that exact moment, at the exact frequency, and they were the exact right place, then no one would see those communications.
What's now, the one in Contact? Isn't it like Hitler going off on one in a speech?
Right, so that's leakage. That's not a directed signature. Now, leakage is detectable, but we don't have the ability to detect our own leakage from even the nearest star. So that you can imagine someone more sophisticated than us maybe being able to detect our leakage. But I think when we think about the Drake, since we can't detect leakage, when you use the Drake equation and you're saying, look, we haven't heard from anyone yet. Yeah, okay, well, forget leakage. We can't detect leakage. So we could only detect people who directly send messages, at very high power messages. That's as good as we can get right now. And we don't do that at all. And so we can't, this is called the SETI paradox. I mean, it's kind of weird. We're listening for a signal that we don't send. And so there's something bizarre about that whole setup. But anyway, this kind of gets into like dark forest stuff. Like maybe people are very worried. Hawking was famously very worried about transmitting, for instance. Now, in terms of like travel, I think that really gets to the root of the Fermi paradox, because probably the most compelling aspect of the Fermi paradox, which is saying, look, if you plug in some fairly even lowball estimates for this, you should end up with a huge number of civilizations. Then where is everybody? Why don't we see evidence? Now, you could counter and say, well, what do you mean by evidence? What counts as evidence? Why should you even expect to necessarily see evidence? But if some of them do travel across the stars, and even if they do it fairly slowly, at say 1% the speed of light, then given the galaxy is about 100,000 light years across, it would only take you about 10 million years to traverse the entire galaxy, which sounds like a lot, but it's nothing compared to the age of the galaxy, which is 10 billion years. So you could have traversed the galaxy 1,000 times over. And anyone could have done this in the entire history of the galaxy. And so all it would have taken would have been one mad species to have decided to, at 1% the speed of light, just send out some it could be anything. It could be, colonizing, or it could just be kind of the grey goo nanobot scenario or something. It's not that hard to imagine someone just being hell-bent on, using the galaxy for resources that would come into, it kind of puts tension on the fact we exist at all. And so this was kind of the root of the Fermi paradox in its original form. It's called Hart's factae, that we haven't been turned into grey goo yet. We haven't been colonized yet, at least as far as we can tell, we haven't been colonized yet. So this was, I think this is basically the strongest limit we have, that this hasn't happened in the solar system. And when you talk about the fact we haven't heard a radio signal, I don't think that's a particularly strong limit. But I think the fact the solar system hasn't been colonized yet does place some interesting limits on the frequency at which one might expect people to be traversing around the galaxy doing this kind of stuff.
So what is the grey goo hypothesis?
Oh, I kind of just mean like a nanobot, like self-replicating nanobot landing on a planet and just going around converting planets into computer substrate or something. So this is kind of like post-singularity type arguments that, eventually once we hit singularity, you just want bigger and bigger computers, since that's kind of the name of your existence after that point. You would turn the entire planet into computer substrate, and then what are you going to do next? You're just going to spread out. And some people imagine it really happens at the speed of light. There's some wave that spreads out at the speed of light, which is essentially converting all inert matter into smart matter after that point. But that clearly hasn't happened, right? Because otherwise we wouldn't be here to talk about it.
Yeah.
We're really getting off into some interesting stuff there. So within that, I guess, is the question. There's a couple of questions that I found really interesting from that. One is thinking about, again, we said that the Drake equation is deeply flawed, but thinking about what the additional multipliers on the end of that would be to think about things coming to visit us. So the Drake equation being designed for there being technologically advanced species. I guess the multipliers on the end would have to be things like, are they interested in visiting us for whatever reason that might be, whether it be colonization, to study us and stick things up our bottoms, apparently, or whatever reason it might be, for the resources on Earth, whatever it might be. And then there'd have to be another multiplier, which was how often do you go from radio to some sort of ability to travel those distances, which we currently, I don't know, I guess we don't really have that in any sort of sensible sense. I guess you could stick a load of people on a barge and try and send them, but we don't have it in any sort of real sense. Those, I guess, would be the multipliers that you would have to put on the end of that equation. And
although it doesn't have to strictly be a multiplier, because you don't have to be communicative, right? You could be the silent type that just spreads across the galaxy that way, and you don't actually send out any radio communication.
Yeah, so I guess you'd be stripping out that radio one and changing it for a different multiplier. But I guess, again, it's so hard to know because we haven't moved on to those technologies yet. How long it takes to go from emitting radio waves to building barges that travel across the galaxy. There's no way for us to get. And I guess it's also coupled with L, right? Because if you don't hang around long enough, we're seeing the problems on our own planet with climate change, for example. If you don't hang around for long enough, there's a limited window in which you can develop those technologies. So I guess some of the things in here are also interdependent. They're not necessarily completely decoupled constants.
Yeah. And Ramsey, do you have something?
Yeah, you could. I think, Sam, you can swap out quite easily, like transmitting radio with developing electronics. There's quite a relationship there between getting electricity going, getting electromagnetism going, and then getting to electronics and compute power. So you could probably fiddle with that one a bit.
Trying to think of the little pathways on civilization, which ones you get and then which ones you're allowed to get afterwards.
Well, I think if you have a civilization that spreads out, I mean, the resources thing I really don't buy, because there's just tons of planets out there. There's no reason to pick on the Earth out of all the planets. The only reason to pick on the Earth would be because we're here. That's pretty much the only thing which seems special about the Earth. If you want water, there's water all over the solar system. Way more water within within Ganymede than there is on the Earth. So that would be the logical place to go for water. And water is an extremely abundant chemical in the universe. So there's just no, these entire gas giants we've detected just full of the stuff. So there's no shortage of water, which is often like a popular sci-fi trope that they come here for our water. But but in terms of, it gets really interesting when you think about a colonizing civilization, because then you have to think about cultural effects. And as long as we believe the speed of light is a finite limit, then having civilizations which were once all spawned from the same originating civilization. And if you ever read like The Foundation by Isaac Asimov, this kind of gets into this kind of stuff, and there'll be the show about it soon. The civilizations end up so far away from each other in terms of light travel time that they just sort of develop into independent cultures. And at a certain point, do they even know that they were originating from the same? They might have incredible similarities to each other, but ultimately they don't necessarily recognize each other as the same culture anymore. And so you get into these kind of waves of spreading out, and then some can have economic collapse and retreat. And so there's quite a lot of simulation work that has been done. Just at the University of Rochester recently, there was a new simulation that came out where they create this beautiful movie showing this wave of propagation across the Milky Way galaxy as it spreads out. And it just happens like in a snapshot. If you play a video of the Milky Way, like everything's uncolonized, and then just at the speed of like 1 second per 100 million years or whatever it is, just suddenly like the entire galaxy is just completely changed. And after that point, you've got a very different galaxy, as I said, with all these different cultures and things going on. But we don't see any evidence for any of this. So as far as we can tell, we seem to live in a pre-colonized galaxy scenario. Maybe we're the first. Some people hypothesize we might be the first. Or, when we think about interstellar flight, we're not thinking of sending people. I mean, sci-fi films do, sure, but the sorts of craft we're thinking about, and we actually have a project in my group, we're working on this as well right now. It's kind of top secret, but we think about tiny stuff. Because the lighter the thing you send, the easier it is to get it up to relativistic speeds. And so you want to send something that's like a microgram, or even a gram at most. That's sort of the size that the Breakthrough Starshot is thinking about sending to 20% the speed of light, is a gram-sized microchip. And then when you're talking about very light things, you can accelerate them at very high speeds. I mean, just the g-forces of acceleration we often talk about for this would completely annihilate any human being. There's no way you could survive that. And so when we think about interstellar flight, at least in our extrapolation, which who knows if it's a useful extrapolation, but our extrapolation is that we're moving towards probably sending AI digital versions of our intelligence, in essence, in the lightest format we can possibly send it.
You were talking, Dave, about shortcutting this equation, which obviously is a sensible thing to do and go directly to the source, as it were. What, if any, are the kind of scientific ways that we might look for life on an exoplanet without actually going there? Obviously, we don't have the technology to quite go there at the moment, but we might be able to look at molecules in the atmosphere, things like this. What would be potential signatures? I'm sure there's been some work done on what. Oh,
there's lots. Yeah, there's lots of work on that. So I was part of a workshop a couple of years ago, just about a year before COVID hit, and it was called the NASA Techno Signature Workshop, where we got lots of people together who think about this. And we put together a massive report that I helped put together that lists pretty much all the things we know of that could be a possible sign of technology. So there's a long list in there, but things include, as you said, so one example would be CFCs put into the atmosphere. Nitrogen dioxide is a pollutant as well, so these shouldn't really be hanging around in an atmosphere. The climate change that we're seeing is another signature. The carbon dioxide levels are elevated, and the rate at which they're increasing is unnatural. Particularly the derivative is unnatural. The heat island effect in New York City is a technosignature. If you could do thermal mapping of an exoplanet and you see these giant hotspots listed across the coast, that's cities. That's what it is. You can even look at satellites. So, for instance, we're putting a ton of satellites up right now with Starlink. And they can even start to create basically an artificial ring system around the planet that you could detect. And especially if they're geosynchronous, that would be a dead giveaway they're artificial, because geosynchronous, they orbit with the same revolution rate as the Earth's spin. And so that's just a really bizarre coincidence. There's no natural reason why debris would get trapped into that configuration. The only reason you put something there is to monitor the Earth. That's it. So if you see a ton of satellites and a ton of stuff in geosynchronous orbit, that's very suspicious. So there's a long list of these things, and they vary in terms of how, there's a lot of xenopsychology going on here, right? You're sort of guessing, well, we do this, so presumably they would do this. And it becomes, I think the counter argument is that this is somewhat contrived. We're guessing at the minds of some entity that could be so alien to us, they just might not think remotely in the same way we do. But I think a basic characteristic of our nature is that we are basically unsustainable, as we've already mentioned. We're destroying our planet. We're in disequilibrium with our planet, very much so. And so either we will have a short-lived existence of being in disequilibrium, and that'll be the end of us, or we'll eventually find out an equilibrium where we're completely sustainable. And if we're completely sustainable, you basically knock off a lot of those technosignatures off the list. And so long-lived civilizations could actually be the hardest ones to detect. Because they're in complete balance with their natural ecosystem, and you just can't tell that they're there. So that's called another paradox, the sustainability paradox in SETI, that we expect civilizations ultimately, the easiest ones should be long-lived to find, just temporally. That gives them more chance to be found, but paradoxically they'd be harder to find by the sustainability paradox.
I saw a video that you did which said something along the lines of, we could be surrounded by long-lived civilizations, or there's a possibility that that's the case. Is that going along those lines? Is that kind of argument that if you become a long-term sustainable society, then you're more likely to be the ones that are hanging around in the galaxy?
Right. It's really just looking at that tail end of a distribution. So you imagine there's some exponential drop off. There's lots and lots of short-lived civilizations that just annihilate themselves, and then fewer and fewer ones that last a long time. And that just makes sense from a, if each year in your existence there's some finite probability of annihilating yourself, then there's going to be less and less ones as you go up the ladder to long and longer lived civilizations. So naively, you would expect there to be very few long-lived civilizations, but it's like walking into a forest. There could be most of the tree, there could be some very, very old trees in there that you're only really looking at because they're long-lived. And the species which they are owing to, which gives them their long lives, could be inherently a rare species to be born. Like if you look at all the seeds falling onto the forest, very few of them correspond to this long-lived species of tree. But when you actually look in the forest of the trees which are actually there, about half of them are the long-lived ones, just because they last so much longer than the short-lived ones. They just tend to dominate over time. And so that same effect may be playing out. We argued in this paper, a couple of colleagues of mine helped me put together, that suggested, the temporal advantage of these civilizations means that if they last, we kind of calculate an upper limit, I think, that if they, as long as there's some truncation effect, as long as there's no truncation effect, which kicks in at about 2.5 times our current lifetime, then we should be surrounded by longer-lived civilizations rather than shorter-lived ones. If there is a great filter which is about to hit us, and the maximum civilization lifetime is 1.1 times us, then that assumption is wrong, or that conclusion is wrong. But if it's greater than 2.6, which isn't that much longer, then actually you would expect most civilizations around you, not necessarily communicating with you, but just the ones around you, to be older than you, by that sort of forest analogy.
I don't know if you can see this paper that I've just brought up on the screen, which I believe is one of yours as well. So as we sort of come towards the end of this, I want to go into something, some what's the word I'm looking for? Optimistic approach, I guess, to the potential for there to be life in the galaxy. You mentioned there that civilizations, it would be likely that they have this sort of exponential die-off, where there's lots of short-lived civilizations, probably less longer-lived civilizations. But I've seen one of your papers about the birth-death paradox, or the birth-death formalization, a different telling of the Drake equation. And in there, you suggest that these civilizations are popping out kind of on a Poisson rate, and you have this exponential die-off of the civilizations. And if you mesh those two together, it actually suggests that you're more likely to be living in a period that is busy in the galaxy. Is that fair?
Yeah, that's correct. Yeah, so it's a pretty simple argument, but if the average rate of civilizations in the galaxy is 3, and that's really what the Drake equation is it's the average number of civilizations. It's not actually supposed to be the actual number at any one time, because all of those terms are averages. It's the average number of stars with planets, the average number of planets that are habitable. So so you get this number, which is the n, it's the average. Let's say it's 3, but it's kind of like anything. Everything varies across an average. I mean, it's never just going to be equal to precisely 3 at all times. There'll be some times when there's 4, sometimes when there's 2, just due to randomness in the galaxy. And so we can kind of show there's a good argument to show that they should be Poissonly distributed, which is the name of a particular type of distribution. And what that means is that the most likely is 3. And then you've got 2 and 4 just to the side of it, and they're actually equally likely. So it's equally likely that you could have 2 civilizations in the galaxy as 4. But which of those 2 galaxies are you more likely to be born into? Are you more likely to be born to a galaxy that currently has 4 civilizations, or a galaxy that currently has 2? Well, naively, it's like comparing populations of countries. You're more likely to be born into a high population country than a low population country, and so you're more likely to be born in an epoch. These are like countries in time, almost. You're more likely to be born in an epoch when the galaxy has a high population than average.
So even though there's an equal probability of there being 2 civilizations or 4 civilizations at that particular time, given that you are alive,
over all times, it's equally likely to have 2 or 4.
Yes, but given that you're alive at this moment, you're more likely to be alive in the 4 than the 2, because 4 is bigger than 2.
Yeah.
Interesting.
So you end up with a positive slope. So yeah, you end up with a bias towards living in busy periods overall. So that's the only source of optimism I've really had. So I'm glad you highlighted that, because that does give me some hope.
I was watching your video, and I remember you saying that this was one of the grains of optimism for potentially there being life in the galaxy. Is this argument from a kind of mathematical standpoint with the Poisson distribution. Dave, as we sort of come towards the end of this, maybe one more note of optimism. We talked about, and Ramsey, you can probably jump in on this, the technology of going from one planet to another. Obviously, with this report, with the UFOs, the UAPs, the things have to get from a technologically advanced planet to our planet. Are there any studies or ideas as to how a technologically advanced civilization might do that? I've seen a couple of your papers, videos on how a civilization might be able to traverse those huge distances between, and maybe that's another source of optimism, that people are thinking about these ideas and how we might possibly be able to go to these places one day.
Yeah, I mean, it all depends on timescale. So if you're willing, I mean, Voyager 1 and Voyager 2 are interstellar spacecraft. It's just, we don't normally call them that, but they are traveling through interstellar space, and over, I don't know exactly what fraction of C they're moving at, but over several billion years, they will cross a very significant fraction of the galactic radius. So we've already built, to some effect, interstellar space. Anything that leaves the solar system is by definition interstellar. Now, if you want to go faster than that, we did this paper that was looking at sort of natural accelerators in the universe, and we suggested black holes could be one way, neutron stars, which Freeman Dyson was very interested in. So if you had a nearby black hole, black holes aren't actually that rare. I mean, the problem is there should be one within about 30 light years, but we just can't see it because it's a black hole. So they're actually very difficult to detect, of course. They're extremely tiny objects. The event horizons are extremely tiny, and so there's very hard to spot them. But in principle, there could be one pretty nearby. Even Planet 9 has been suggested to be a possible micro black hole, like a primordial black hole. And if you had something like that, that would really help you out, because that essentially provides kind of a free accelerator. And then, I see you got like the warp drive picture up here, and there's certainly, the Alcubierre drive, the famous paper that suggested that there's a solution to GR that allows for this kind of warping of space, as we've seen in Star Trek, that could allow potentially to travel faster than the speed of light. Now, when that paper first came out, I think the energy required was like greater than the amount of energy in the universe or something. It was just some ridiculous amount of energy. They brought it down to sort of, with refinements, to sort of like a Jupiter mass worth of energy. So, equals mc squared of Jupiter. So easier, but and maybe by that trajectory, you might imagine it will eventually become feasible. But of course, there's lots of problems with this that have been pointed out in the literature. Things like Hawking, you get bombarded by Hawking radiation inside the shell. You kind of need a warp drive to build a warp drive. There's like a chicken and egg problem that gets set up with these things. But to me, one of the worst things about it, why I'm very skeptical about warp drives, is it breaks causality. And so you could actually send messages to yourself in the past with a warp drive. And this is just because the idea of simultaneous events in SR and special relativity, like there isn't such a thing as a unified agreed upon definition of now. It depends on your motion. And so if you have someone flying off at high speed and they're moving at say 90% the speed of light, then they'd be sort of time dilated by a factor of 2. So if they send a message to the Earth, then the Earth could process that message and send it back, and you can actually end up with this loop where it sends a message to the ship before it leaves and to the Earth before they receive the message. And so you can break causality. It's very non-intuitive. I really would, I think I should do a video about this at some point to try and explain it. But essentially, you have a time machine. Whenever you have a warp drive, you always have a time machine. And
I seem to remember a study that was done, Dave. This might be useful for your video as well. At least from a humour perspective, if not from a serious science perspective. But there was a brief study that was done on Twitter a couple of years ago, where they were trying to work out if anyone had sent a message about a particular event before it had happened, and they went through billions of tweets to try and see if there was any mention of certain great world events that had happened before the thing had occurred, and they obviously,
that's like kind of Nostradamus style.
Exactly.
Because if you go through Moby Dick, you can find sentences, or like you can find patterns, right? If you take like every 12th letter or something, and then skip every fifth one of those, you can like come up with some arbitrary rule that eventually reconstructs sentences like Bill Clinton will be president in 1993 or whatever it was.
I remember watching one of these on like the Bible code or some ridiculous thing.
Right, in the Bible, yeah, it's classic. So, but that's just smashing a very large number of characters within a very aggressive algorithm. There's nothing in that. That's just monkeys on a typewriter eventually writing something that seems coherent. So yeah, you have to be. I'm a bit worried about if you go through billions of tweets. I think you might end up with the same effect. I could believe you could claim something was significant, but you have to account for how many times you've searched and how aggressive you were with your algorithm.
I think Ramsey, you had a question as we sort of come to the end of this about a particularly controversial observed object that might be some sort of alien technology. Maybe if you want to.
Thoughts on? Do you mean thoughts on Umaru?
Yeah, I can't. This is why I've thrown it to you, because I don't know how to say
it. Our famous visitor from a couple of months ago, Dave.
Wow, whatever it's called.
Yeah, what were your thoughts on that? Was it a cigar-shaped rock?
You mean Oumuamua?
Okay. Yeah.
I was trying to think exactly what you want me on
that. Dave, that's what I said. Wow. Yes.
Oumuamua. Yeah. Look, as far as we can tell, that thing's completely natural. It's definitely, it seems unusual, but it's unusual relative to the solar system asteroids. But we don't really have any good reason to think that interstellar asteroids should necessarily be representative of the solar system asteroids. So it has kind of a slightly curious shape, but there are asteroids in the solar system with similar aspect ratios. Not a lot, but they do exist. So natural processes can form asteroids like that. It's also thought, for example, one of the best ways to get an interstellar asteroid would be to like do a slingshot essentially around your star to get really close to the star. And that would kind of tidally rip the object apart. It'd be like spaghettification. So if you had a spherical object, it would actually naturally get strung out into that kind of situation naturally, just by virtue of being interstellar. And then you look at some of the other properties, such as its speed. I mean, a lot of it has been made about the fact it's moving close to the local standard of rest speed, but that's probably what you would expect, I think, because these systems are probably, an interstellar asteroid is most likely to be ejected very early on in the solar system's formation, because that's when things are most chaotic. We had the heavy bombardment in the solar system during that period. We've got just asteroids flying all over the place. Jupiter was moving back and forth, flinging stuff out. And so if you're going to fling something out of a young solar systems by definition form in the LSR, in the local standard of rest. And so it makes perfect sense that an object that was flung out of a young system would be moving close to that speed. So, yeah, I think you can go through all of these suspicious things about it, and you can certainly find quite plausible, in my opinion, natural explanations for all of them. And so I would need a very high level of proof, of evidence, to convince me that something was truly of alien origin, especially when everything about it appears completely natural as far as we can tell.
I've spent 2 weeks looking at this SARS-CoV-2 stuff, and it's amazing the sort of little things people will pick out to try and say that this is the hand of an intelligent designer. It just seems to be almost a sort of biblical argument that people get to it. They just take a little crumb and then suddenly make it fit for this to be.
Yeah.
I vaguely remember there was something about it accelerating away. Didn't they think it might have been a solar sail because?
Oh yeah, there was an acceleration effect. Yeah, and that's also been seen actually for other asteroids as well. Well, really for comets, especially because they tend to outgas, and that speeds them up a little bit. And there wasn't an obvious cometary tail of this object, and so that was thought to be somehow inconsistent. But the level of acceleration is consistent. It's very, very, very small level acceleration. So kind of the level you'd expect from outgassing. And it may just be, when we monitored it, it was going by very quick. We weren't able to capture data at all wavelengths. So there was a paper published in Nature that showed that there were some gases that may be being expelled that we just had no sensitivity to even detect in the first place. And that could plausibly explain the outgassing acceleration. So I think we have reasonable explanations for what it was doing, but of course there's lots of questions, and I think I'm not gonna pour cold water in the idea of at least considering the hypothesis. It's certainly interesting to consider the hypothesis. I think it's worthwhile to consider it, and eventually we should go visit one of these things. The next time one comes by, we really would like to intercept it, take a sample, take photos on the surface and all this kind of stuff, and then we'd really understand what was going on with these objects. But I think for now, we just have kind of like UFOs and UAPs. We have pretty poor data on it, and you could fill in that poor data with aliens if you wanted to, but you can also equally explain it with natural explanations. So I don't see a strong case, in my opinion, for aliens.
You made a very interesting point before about if you were going to send something, you'd send a microscopic gram-sized object, and I think that's one of the least likely things about the reported UFO visitations. The idea that some grey alien steps out and isn't already dead from the journey, or running out of food, or having its craft punctured by a very, very fast moving object on that massive journey. And I think it's way more likely that yes.
Well, you need new physics. That's the only way you can do it. There has to be some physics we don't know about. That can explain this, and that's possible, but it's another level of complexity that you have to add to it. And Mick, I'm sure, will tell you all about the UAP videos. He talked to my channel for a little bit, and I think when I certainly look at them, I don't see evidence for something which cannot be explained by our laws of physics. I don't know what those objects are. It's really interesting what was going on. There's some clearly curious phenomena occurring, but I don't see evidence for something which is moving in ways which cannot be explained by the laws of physics as we understand them.
Ramsey, did you have any more questions for Dave before we kind of close up? Because I know he has to run off relatively soon.
Well, the only one I still had written down is everything we've discussed about what all of these things might be and what the answers to the Drake equation could be. There's that one other remaining hypothesis that people talk about that I think has been gaining some popularity, which is that we're all just living in a simulation anyway. So I don't know what your thoughts are on that particular theory for why we're here talking about this today.
Yeah, I read a little paper about that as well, and I did a video about that one. Yeah, but essentially, I'm fairly skeptical about it. It's really difficult to refute. In fact, it's arguably not scientific because it's arguably not refutable to any degree. You could always engineer the simulation in such a way that there's just no way to tell, and so then you basically fail the test of it being a scientific hypothesis at all if it's untestable. But regardless, I think you have basically two scenarios. Either the natural world is the natural world as we know it, which is consistent with our existence. So that's perfectly probable. And then you have, we live in a simulation, but we just can't tell, which is also consistent with our observations and perfectly probable. So you have these two almost equally likely scenarios, but I would say that the simulation hypothesis is inherently more contrived, because then you don't just have nature, you have to have nature still in the simulation hypothesis, but then there's someone with a computer that's simulating us. So you have an extra level of complexity. In fact, of many of the simulation arguments, there's like levels nested within levels. It's like Inception style kind of thing going on, a hierarchy of realities. And so that's just by Occam's razor, that's a less likely, all things being equal, because they are equally likely, they equally appear probable compared to our observations. You would always, from a scientific perspective, favor the simplest explanation. So I can't prove to you it's wrong. I'm not going to claim that, but I just think if I had to bet on the odds, I would say it's unlikely, because again, there's no evidence either way.
I always see people using these kind of simple ideas that I see anyway, is that the speed of light is the sort of the finite processing speed of the computer that's running the simulation, and that quantum mechanics, the fact that you can only sit in certain levels of energy or momentum or whatever it might be, is the quantization of that simulation. I'm sure you've come across those kind of discussions. I mean, I don't really put much stock in them, but these are the arguments that I've heard people kind of use on that front.
Right, but it's the same thing really, because you're saying that the speed of light could be explained by simulation hypothesis, or the speed of light could just be, encoded as a natural phenomena in the universe. We have no reason to think there's anything wrong with that as an alternative hypothesis. So, I can't, and with the simulation hypothesis, you have, again, more contrivance, because then they're still living within this sub-reality of the nested realities. That's at least, an extra level of complexity to add. So, unless there was something that you just could not explain, like I think if you found out, there was some message written in the sky that said, "You are simulated," the stars just moved into that position. There's no way we could explain that with the laws of physics as we understand them. So that'd be pretty convincing proof that we live in a simulation.
So the aliens are going to tell us we're in a big Truman Show at the end.
Yeah.
So it's going to be. So let's close up, Ramsey, unless you have anything else to say.
No, it's great. Thank you, Dave.
Yeah, Dave, thank you so much for taking the time. Dave, you've talked about a lot of the interesting papers, a lot of the interesting topics that you talk about. Where can people best keep up with the work you're doing and the things you're saying?
I guess if you really want to hear me speak more, you've probably heard enough of me speaking by now. Really want to hear me speak more, you can head over to the Cool Worlds Lab YouTube channel, or just Cool Worlds, and you should be able to find us. Yeah,
I really suggest you do that. Dave makes some excellent videos, really, really interesting, really, really deep topics, and he puts a lot of time into making those, and he's doing really, really well. I'm very proud of you, Dave, although I'll never say that again. Dave, thank you so much for taking the time. Again, we really appreciate it. I know Ramsey does as well.
My pleasure, guys.
And
cheers, Dave. Thank you.
Yeah, have a good weekend, and let's talk again soon when the next thing comes down the pipe.
Sounds good. See you guys around,
buddy. See you later.
Bye.
Bye.